Hello everyone, this is Ashish. Welcome back to Spacecast. Today we are having a lot of fascinating topics to discuss. The general regular viewers of Spacecast understands that it is a unscripted podcast, but at the same time very well researched podcast. I do not explain anything over here which I have not spent weeks and sometimes even months studying. A lot of it is also, most of the time, something related to my past experience of working as a scientist in ISRO or Department of Atomic Energy. So there are a few topics, but at the end, these are what we are going to be discussing. If you're on YouTube, you can also find in the description box. If you're not, maybe some audio platform, these are the timestamps. Basically, this is how it went, but I would suggest that you go through the entire version, because what Spacecast ultimately is what I always wanted to have as a podcast. Always an enthusiast of space science, always an enthusiast of engineering. I wanted to listen to technical things talked in a casual, friendly manner while I'm, let us say, working out or traveling or in any point where my ears are free. So that is what I wanted to create over here. Hopefully I'm doing a great job. So let's get into the topic right away. So initially I wanted to start discussing with plutonium based reactors, because in the last one, in episode 11, we talked about the birth of nuclear science and engineering. We talked about the Hiroshima and Nagasaki case, and that was majorly at the later half of the last podcast. But I promise that in the next one we are going to start talking about how nuclear power is generated, how nuclear power plant works. Those are the things that we want to discuss over here. But in the last podcast itself, somewhere I said that something like related to 3 moons on a planet, and I got a fascinating comment in the comment section. And like I've said before, I do go through each and every comment. You can see it right now in the comment section as well, because there will be a reply or response to every comment there is. Now, SMIT Smith Bose, I don't know if it is his real name or not, says that at 10433 just researched and found out that only 2 known celestial bodies, specifically exoplanets with exactly 3 moons, namely J1407b and Gliese 667bd. Now, I'm not doubting his research, but I did a sufficient amount of research on this as well, specifically on NASA website, NASA exoplanet website to be precise. And none of them actually have been proven to have 3 moons, but it is fine because he brought 2 different names and both of them are fascinating in their own manner. Both of them are relatively close to where we are standing over here. I think Gliese is somewhere around 60 to 70 light years away, and J1407 is somewhere around 400 light years away. I'm going to be discussing it in more detail in a moment. So let us get into it. First, we are going to start with J1407. Now, these names are very complicated because these have been recently discovered. For example, this J1407 has been discovered in 2012. So it will take its time to get them names like Saturn, Jupiter or something. And speaking of Saturn, J1407 is exactly like Saturn but 200 times bigger, and that's what makes it so fascinating. Up until we were exploring our closed universe, Saturn was the only celestial body with such an extensive ring pattern, but this one beats Saturn by a mile away. For example, if you place this, so how it goes is that J1407 is the sun, or in a better way, a star which is very similar to our star around which our planet is revolving, that is sun. Now, J1407 is a star which is very sun-like. It is 90% the mass of our sun, and around that is a planet which is revolving, and that is J1407b. So that is how generally it goes. Like the star name will be similar to the planets orbiting that star. I'm going to be showing you some of the pictorial depictions. Spacecast is always better on YouTube with the video version, but I'll do my best to clarify things for the audio version as well. All right. So as you can see, these rings are massive, and the largest one, the outer periphery, is 120 million kilometers. If you want to get it to a proper perspective, the diameter of Earth is 12,000 kilometers and the diameter of Saturn is 270,000 kilometers. So it is 200 times the rings of Saturn. But comparing the size is not sufficient. If you compare the age of Saturn and J1407, J1407 is only 16 million years old, whereas Saturn is 4.5 billion years old. So this is what scientists are thinking, that for the first couple of million years, these rings are going to thin out, and some of them are going to turn into moons or natural satellites. And that is what they are also thinking, that maybe in the initial phases, even Jupiter or Saturn were having rings this massive, and over time they turned into natural satellites. And if you place J1407b where Saturn is right now, you will be able to see it from Earth with your bare naked eyes, and it will appear to you multiple times larger than Moon. Isn't that crazy? In terms of distance, it is 434 light years away. So whatever you are seeing right now is obviously something that happened 400 years ago. But that is the fascinating thing about this, that this is the first celestial body that is found outside of our solar system to have such a ring-like pattern. And the star that it is revolving around is not that bright. Matter of fact, most of the time it eclipses that star when it is somewhere in the middle of your position and the position of that star, that is J1407. So if you look at a line of sight in which you are at one end and that star is at the other end, and this planet J1407b is in the middle, it will eclipse almost 90% of the light coming from that star. And they did a very amazing visual depiction. So you must be thinking that, oh, did we really see the rings from down here from Earth? By the way, this was first discovered by an astronomer in Rochester University. I'm going to discuss more about that. An article which is exactly the same is published both in the website of University of Rochester and the NASA Exoplanet website. Just in a moment, I'm going to discuss that. But first, going to the Rochester University, you can see over here, they have made a video of how they found out that these are actually rings. Because from here, it won't even appear like a disk. It will be something that will be blocking light. But how do you really understand that these are rings and there are gaps in between these disks? So if you look at this video over here, you can see that star J1407, when is covered or eclipsed by these rings, the lights are higher at some positions and then it goes down back. So there are thicker rings, there are thinner rings, and then there are spaces or voids in between the rings. And that is how you really understand that this is not a disk blocking it, it's a planet, and around that there are rings of basically space debris. And it is massive, and also it is a gas giant at the center of it. All right, let's get into this article that they have published over here. Astronomer Eric Mamajek at University of Rochester and his co-author from Leiden Observatory, the Netherlands, have discovered a ring system that they see eclipse a very young sun-like star, that is J1407, is of enormous proportions, much larger and heavier than the ring system of Saturn. The ring system, the first of its kind to be found outside the solar system, was discovered in 2012 by a team of Rochester's Eric Mamajek. A new analysis shows that it consists of over 30 rings with tens of millions of kilometers in diameter. Like I said, the largest one is close to 120 million kilometers. Now, if you also want to put that in perspective, I think the distance in between Sun and Earth is somewhere close to 140 million kilometers. So let me just confirm that. Yeah, 150 million kilometers. So you can think about it like that also. So if it was placed where the sun is placed, it will be almost reaching where the Earth is, but also much smaller than what our sun is. But you can understand how widely its gravitational field is influencing the dust around, that it is actually forming it into these rings. Also, there are fascinating things that this planet might be having a moon. That is where the comment actually came, that this is having 3 moons, which is not what I could find so far, but we'll get into that. Alright, so this is what I was saying about rings becoming thinner and thinner over time. Astronomers expect that the rings will become thinner in the next several million years and eventually disappear as satellites form from the material of the disk. The planetary science community has theorized for decades that the planets like Jupiter and Saturn would have had at early stages disks around that them led to the formation of satellites. Okay, that we understand. That earlier we are expecting that even planets which we do not see today having rings might be having at that time rings, which over time turned into the satellites. Astronomers estimate that ringed companion J1407b has an orbital period of roughly a decade in length. My god, 10 years of revolution. The mass of it has to be, because it is so huge. Like I said, the distance between the sun and close to that what we have Earth as. All right, the mass of J1407b has been difficult to constrain, but most likely it's in the range of 10 to 40 Jupiters. So it is not a small planet at all, and it is like larger than Jupiter, so definitely larger than Earth. I tried to find out some graphical relation to it, but this is a very early discovery and people did not do a lot of work in this domain. If you have more findings related to J1407, let me know down in the comment section. Yeah, that's what they are saying next. The researchers encourage amateur astronomers to help monitor J1407. So every time it reaches that position, right, where it eclipses its own star, that is where you can find more and more about this particular planet. Also, I can actually contact the author. I'll try to do that. Let's see what response we get from this one. Maybe we can have him or her on Spacecast. I'm not sure. Lenore Sierra, probably she is the author. I can get more information. I'll see about that. Also, if you have more information, let me know about it. But it's a fascinating topic, and I'm always happy that someone puts some input like this in the comment section so that I can find out more about that. Now, in a similar manner, I have another thing, that is Gliese 667, about which I can really talk in brief over here, and mostly I can show you a lot of visual representations because it is available at exoplanets.nasa.gov. Matter of fact, most of you guys, I'm pretty sure, were not aware of this gold mine that is available for free, to be accessed for free to everyone. All right, so if you are on YouTube, it would be great if you can just check out the video version of this part. So this is how it is represented over here, GJ667c. It is quite fascinating. It's again a 3-star system. It's a triple star system, which is just 23 light years away from Earth. So what you are seeing right now is close to what it actually was in 2000 or 1999. So it is not far away at all. Now we have talked about what was that, Alpha Centauri, right? Now that was interesting as well. Now this is also a similar kind of star system because it is again a 3-star system. Number one, Gliese 667a and Gliese 667b are at a distance of 13 astronomical units, and 230 AU away is Gliese 667c, which is the most big area of interest over here. It is actually a red dwarf which is having the mass of 0.35 or 35% the mass of sun, luminosity of somewhere close to only 1.4%, that is 0.014 solar luminosity. The other two are pretty massive, that is Gliese 667a is having 73% of solar mass and 13% of luminosity. Gliese 667b is having 69% solar mass. It is 5% solar luminosity. All right, so they are very, very dim, and also that makes sense that it might be very young. So let us get into Gliese 667c and pay attention at the system over here. So earlier there were less discoveries about this, but now we know more, that more and more planets are revolving. So you can see over here that there are in total of 6 planets revolving. No, 5 planets revolving, and the 6th one is the star. So if you look at the star, this is the star. And this website is so amazing that you can actually compare it. So this is the sun. It does appear smaller, and as you can see, it is not really a star like sun. It is a red dwarf. All right, and as you can see over here as well, it is 24 light years away. Now coming back to the system again, it is said that it might be having as much as 7 different planets revolving around the star, but so far NASA has been able to mark 5 of them, and you can check them out as it is given over here. So it is G667c, B, C, E, F, and G. And that is what I was not able to understand, because the guy who was commenting was talking about D. So NASA has not put information about that. But let us compare these planets with our Earth. So as you can see, these are much larger than Earth, and it is, although larger than Earth, it is much smaller than Jupiter. All right, most of them are gas giants as far as what we can say for now. And that is what I'm saying, like these systems are at a very infant stage of their journey, and over millions and billions of years these will turn out to be something like us, because these are pretty much at a very perfect location for you to live properly. So for example, this Gliese 667cc, I'm going to focus on that over here. This is kind of a habitable zone. So this is a hypothetical visualization that you are seeing over here. It is kind of a habitable zone because it receives 90% of the light that Earth receives. Let us compare it with Earth right now. Yeah, it is larger than Earth, but the light that it is receiving is somewhere close to 90% of what we are receiving over here. And the main reason for that is that Gliese 667 is much dimmer. Now, there was a YouTuber, I'm going to give credits somewhere in the screen right now. He basically discussed about how these orbits are very small. So you can see this is the orbit of Mercury, and these are orbit of all the planets that are revolving around this small star. So they are very close to their own star as compared to what we are having in our solar system. And this in particular, the planet C, is having a revolution of only 28 days. So that is how their 1 year looks like. In 28 days it is done. The main reason would be the orbit is much smaller. This planet also shows sign that there might be presence of H2O. Now these are all the reasons why people are thinking that it is in one of those habitable zones. So what we are looking at is the planet which is second closest to its star. And this one, which is the closest one, let's pay attention towards that as well. This one looks beautiful, without a doubt. It is 6 times the mass of Earth. So if you compare that with Earth, this is the Earth, and this is your purple planet. Looks beautiful, doesn't it? I'm just going to show you quick views of other two. You can, by the way, go to the website and check it out yourself. There's an abundance of information. You can go through it one by one. One problem with this one that I would like to mention over here, and let me bring it back. Where did it go? Yeah. One problem is that it does not actually have a rotation. You get the point? It has a revolution around its star, but it does not have a rotation. So one side of it will always remain in shadow, or a bigger problem would be one side of it will always be kind of frozen. And the next side, even though this is frozen, we'll just inhabit over here. But then that side will be super heated up. So you will be having something in the middle over here, which can be called as terminator line, where you can spend some time to live. Golden line, where it will be not too hot and not too cool, where you can live. So that drastically decreases the amount of habitable zone, but at the same time, the places like those will be having like 28 days out of 28 days, very chill kind of weather. Also, since the atmosphere of this will be a little bit thicker, because of that reason, there might be a little bit moderation of weather. These are like far-fetched dreams. Let me see if I can remove this kind of thing. Yeah, there it is. This is your entire planet. All right, that's pretty much about it with the astrophysics part. Now, I would like to discuss these things every now and then. If you have any more suggestions, put it down in the comment section. Matter of fact, you can also join our WhatsApp group. The link will be down in the description box. Just join it. Click on the link. And we have a small community, small group, but tight knit. Everyone who are very enthusiastic are over there. No one is obligated to be over there. So if you are over there, you are interested in this stuff. So that's where we discuss a lot of things before the video is produced. Sometimes beforehand, like when I'm working on it, when I'm doing the research, sometimes I share some of the things, sometimes they share some of the things. That is how it goes. It's a fun group. Other than that, I promised you guys that in the last one that next time we are going to talk about nuclear power production. And in the last one, we discussed mainly about the most basic aspects of nuclear fission and the history of nuclear fission, because you have to, when you're talking about it for the first time, you'll have to understand what is the origination of all of this. And when you look at it, if it does not boggle your mind that this technology is less than 100 years old and still has shaped our world so much, like world would have been different if we did not have nuclear technology. And a big amount of stigma is attached to nuclear energy, about which not completely we are going to discuss today, but some part we can touch. And you can see that countries like Germany has decided to completely shut down any power plant that is producing power using nuclear energy. They have decided to go to the solar or the wind, but we are not going to use nuclear. Now, to a big chunk of part of my mind, that makes zero sense, because nuclear energy is it's a clean energy. It has no carbon emissions from the power production part. It is the most efficient way of producing energy, because it unlocks the energy locked in between the atoms, and that's the finest grade that you can get. Like even when you are burning coal and all, it is a crude way of creating energy. But nuclear energy is the most advanced manner in which you can produce energy. A lot of people are afraid of the radiation and all, and I've talked about this before. Most likely you know about it. I've worked in Department of Atomic Energy, and I've gone through a complete program which they call Diploma in Nuclear Science and Engineering. It's a 12-month program, and they teach a lot about the safety. And the radiation level that is in the outside in the environment beyond the whole dome of nuclear reactor is extremely negligible. It does not cause any problem to any of the citizens living. Matter of fact, they took care of all this before they established any of this plant. But every now and then you'd be seeing people protesting that you should shut it down. This is very common actually. And I understand their aspect as well. For example, you can look at the nuclear disasters that has happened. 3 Mile Island was kind of a small one. It had a kind of meltdown, but it did not turn into a disaster where the core is exploding. But we saw those in Chernobyl in 1986, and very, very recently, that is the one part that is terrifying, in 2011 in Fukushima, and that is in Japan. So if you have seen something in the period of, okay, like we can see that in a period of close to 30 years or so, we have seen a nuclear disaster. 3 Mile Island happened somewhere around 1970s. So who is to say that that kind of disaster cannot happen again? And when you look at these people who are protesting, and you are saying that it is kind of safe, it does not really cause that much radiation, but their argument is that, yeah, fine, while it is operating properly, but what if it goes out of control? And most of the cases, all it takes is a human error for it to go out of control. So these are the arguments of both sides, and I'm going to be discussing it in more details with proper numbers, why nuclear energy is safe. And even if you look at the number of deaths that this has caused, more people actually die because of the diseases that they get from air pollution, which is not present from nuclear reactors at all. Now, there are a lot of other contributors of air pollution as well, but like I said, I'm going to be discussing it with proper numbers. But it is a technology that you can't really run away from, and especially in space domain. Like space propulsion or nuclear propulsion is a part that is still untouched by even the biggest space organizations of this world. And they started it at some point in the 1900s, but then again it got stopped. There are news that it might start again. But when it comes to space propulsion, that whole civilian problems goes out of the window as well, because space exploration is dangerous anyways, and in space any problem like explosion or so will not be causing casualties apart from the one who is riding on it. But apart from that, the main reason why nuclear propulsion is so important is because it doubles the efficiency. Like if you rely on the basic chemical propulsion, then it is again a very crude way of traversing through space, because when you look at the distances that you have to travel and the time that it takes, you are bound to acknowledge the fact that it is impossible with the technology that we are having that we will be able to explore distant parts of this universe. It's just not possible. Right before this, we were talking about all of this, like 24 light years away, 430 light years away. All right, 90% of the luminosity that Earth gets, very good, maybe presence of water. It's all fictional without your development of method of actually transporting to that part. So that is one thing where nuclear research has to be done. And instead of straight up banning it, maybe we can put a lot of effort into trying to fix the problems that are there, right? Any kind of technology will always come with a threat that it might go out of control, but it is multiple folds more when it comes to nuclear. You cannot really categorize it with any other, like thermal, hydel, or even windmills. A lot of people die because of wind energy as well. We're thinking wind never hurts anyone. How does people die over there? A lot of people die just by falling to assemble those things, and those deaths are also to be counted. And apart from that, these windmills, when they go obsolete and when they are not useful anymore, it's not removed at all. It stays over there, stays as a junk over there. So again, don't want to get into much more detail, because the main topic that I want to discuss right now is uranium enrichment, and mainly what is plutonium and how is it different from uranium, how is it formed. Uranium enrichment is itself a mammoth topic. And then again, when we talk about uranium enrichment, we have to talk about this one another threat of any country which is investing towards nuclear power production, and that is, everyone is afraid when a country is trying to produce power through nuclear energy, is because that same technology can be used for nuclear weapons as well. And there's a slight difference between a nuclear power production grade uranium and a nuclear weapon grade uranium, which I'm going to talk more in detail when I'm talking about uranium enrichment. Okay, but first let us get back to what was the reaction that we were talking about uranium-235. So what happens is, uranium-235, which is fissile, there are a lot of isotopes of uranium. For example, uranium-233, which is also fissile. There's uranium-238, which is not fissile at all, but it is fertile. Remember these two words, fissile and fertile. We are going to be discussing it in much more detail. And uranium-235 is the most commonly found fissile uranium. And when I say most commonly, it's kind of misleading, because when you scrap out or extract uranium ore, that ore has 99.3% of uranium-238 and only 0.7% of uranium-235. So any ore that you extract which is having only 0.7% of useful mineral is going to be a difficult business, but you don't really have to worry much, and this is where plutonium comes into the picture. But one by one, we are going to understand. To have a continuous power production, you are only going to need somewhere around 3 to 5% of uranium 235 in that ore. Rest can be 238. It is not a problem. For weapons grade uranium, you are going to require 90% of U235. A simple explanation of that would be, when you are trying to produce power, you are not trying to produce all the energy all of a sudden. So you want a continuous steady flow of energy. So not that enriched uranium is going to do the job. But when it comes to a bomb, it is going to produce all the energy instantaneously all of a sudden to create a massive destruction. And that is why weapons grade uranium has 90% of uranium 235. The fun fact is that the process of enrichment is same for both. It's not like weapons grade uranium is enriched in a different manner from compared to power production grade uranium. And that's the problem. Like whenever a country starts to enrich uranium, then all you have to do is keep enriching it and it becomes a weapon grade uranium. That is why there was a fuss about Iran some time back, that people were afraid, Israel was afraid that maybe it has enriched to that level. Okay, more about that we are going to discuss very soon. But first, I want to get this plutonium out of the way. So when you have uranium 238, all you have to do is bombard it with a neutron, and it is going to give you plutonium 239, which is now fissile. This is the reason why in some reactors you are going to see what we call a breeder. So there will be a core in which uranium 235 layer will be at the center, and around that will be having uranium 238, which will receive the neutrons from the center, and over time is going to convert it into plutonium. Now any power plant which is creating this kind of plutonium has to take a lot of responsibility, because these are weapon grade plutonium. If you look at what I talked in the last one, the second atom bomb that was dropped, that was on Nagasaki, the Fat Man, was plutonium based. So these are straight up weapons grade. And even in a uranium based reactor, U35 based reactor, when you are getting a product out of uranium, this can be again bred to create again a fissile material. So that is also a problem. So even the nuclear waste that you're creating in a nuclear power plant has to be taken care of. It cannot be just thrown away, that some people of terrorist category sometimes might pick it up and convert it into a bomb. That is the biggest threat nowadays, that it is not like a country is going to drop an atom bomb on another country. That has always been there, that is still there. But what if a terrorist gets a hold of these nuclear weapons, and then all it has to do is drop it, because a lot of times their own interest is never understood. right? So let us get more into plutonium. So as you can see over here, uranium 238 is bombarded with a neutron and creates a plutonium 94 239. Now 239 plutonium is fissile and 238 uranium is fertile. A fertile material is one that can be bombarded with neutron to create something which is fissile, as simple as that. And also in that respect, I want to talk about something that is called transuranic actinoids. Transuranic actinoids are products which are heavier than uranium, which is bombarded, which when uranium is bombarded with, is created. I'm going to put some of them on the screen over here. Now these are dangerous. For example, plutonium has a half-life of 24,000 years. That is another problem, that the products that you are getting after a nuclear fission reaction, these products, they are not going to go away for hundreds of years and sometimes thousands and thousands of years. So how can a species which have been developing only for the past 1,000 years, or a technology that has not even been 100 years old yet, be dealing with something that will be staying on the surface of Earth for hundreds and sometimes thousands of years? That is the question, and that is again an argument against the nuclear power. So the only way to get rid of these transuranic actinoids is that you will have to burn it as fuel. So like I said, plutonium 239 is fissile, but it is not fissile just like uranium 235 was. Now, you might have heard me talking about moderator in the last one. So a nuclear power plant reactor has basically these constituents. Number one, it will require a fuel rod. All right, you got it. Second one, it will require a control rod, because every uranium-235 fission gives 3 neutrons, which is going to bombard into the neighboring uranium-235, right? So this is what we call chain reaction. But if it keeps on happening like that, like every reaction is creating 3 other reaction, then it is going to create 9 other reaction, it is going to create 27 other reaction, and that's a chain reaction, that is a bomb. So if we do not want that, then we'll make sure that some of these neutrons that are produced are consumed by what we call moderators. These are neutron absorbers, and this will create the reactor in a critical stage. Critical meaning that it is neither increasing its energy nor it is decreasing its energy. Subcritical means that reactor will shut down over time. Supercritical means that it is a bomb now. So that's how it goes. Now this moderator is the third part, which is used to slow down the neutrons. So when the neutrons are produced, it is produced in kind of a speed of light. It's very close to speed of light. So in that high velocity, it is not useful to bombard on any of the neutron. It will be very difficult to hit a neutron. To hit a neutron, it has to be slowed down. And for that, we use moderators. There are various different kinds of moderator. The simple one would be water. These reactors which use water as moderator are called light water reactors. Or earlier it must be called water reactors, but now it is called light water reactor, because now we have something we call heavy water reactors as well, which is going to have deuterium instead of just hydrogen, which is heavier and it is much better to bounce off the neutrons. And when that happens, well, what they call it absorption spectrum, and that basically means that it will be easier for uraniums to absorb these neutrons. So thus it increases the reactivity. So if you do not have moderator, your reactor will always remain subcritical and over time will shut down. So we use these moderators to slow down the speed or velocity of these neutrons that are just created after the previous fission. But the thing about plutonium is that these are fissile only at high speeds of neutron. And that is why a lot of times these reactors are called fast reactors. These plutonium based reactors are called fast reactors. So plutonium-239 is fissile, but the neutrons has to be at higher velocity. So it is not a problem, because now we are not going to require a moderator. Now this moderator, most of the cases also act as a coolant. Sometimes coolant is different and moderator is different, but in examples like light water reactor or heavy water reactor, these act as coolant as well. How? See, coolant is the most important part of a nuclear reactor. Coolant does what it stands for, like it cools the reactor, but also it transfers the heat. It takes the heat out of the reactor core and gives it over time to the turbine. So if the heat stays over there, that is what we call meltdown. So that was the problem in Fukushima. The pump that was supposed to wipe out the water, heated water from the inside of the reactor core did not work, because the plant no longer had a power supply and the generator was not able to work. And because of that, the water that was in there as a coolant stayed over there and over time heated up into steam. And that is what we call a steam explosion. And over time there was a hydrogen explosion, because at very high temperatures these hydrogens will split as well, and this hydrogen, as you know, is very explosive. Got the point? So the coolant plays a very important role, and almost any disaster that you are going to see related to nuclear power plant, there was some problem or the other with coolant, because if coolant was working properly, there would not be a meltdown as well. You get the point? Because it will be taking out all the energy. But most of the time what happens in a nuclear power plant, if there's a disaster, there's not like 12 of them that we can discuss, but what happens is that because the coolant cannot flow, the core melts down. And core meltdown is a dangerous thing, because now it's all radioactive and it will pass through almost anything that you can think of, because the temperature inside the reactor keeps on increasing. Now you will be thinking that why can't we just switch off the reactor and push down all the control rods, and it will absorb all the neutrons and the reactor has just stopped producing any power now. Now that makes a lot of sense, doesn't it? But there's something that we call decay heat, and decay heat comes because of the small reactions that keeps on happening. So you can press the button and drop all the control rod, and what will happen is that the reactor will now become subcritical and over time will shut down. But that over time is the important part, because it will take some time to completely shut down, and that time it will keep on creating heat, and that heat is called a decay heat, which has to be wiped away. So what happens in a case scenario like, let us say, Fukushima, where earthquake has happened? What if that earthquake knocks off the power grid? So that power grid will be providing power to run the pumps, right? So now if that is out of the picture, how will that pump run to keep on rotating the coolant? So the second answer is the generator. So the generator will run the pump, and then pump will remove all the decay heat while the reactor is shutting down. But then again, what happened in Fukushima is that a lot of generators were downstairs, and because of the tsunami, the generator rooms were flooded. And because of that, generators did not work. So some of the backup generators worked, but over time they also started malfunctioning, and ultimately it turned into a disaster that we all know of. Now, if we talk about what happened in Chernobyl, I'm going to be discussing this in much more detail over time, but what happened in Chernobyl, I'm pretty sure a lot of you guys watched the TV series. So they were trying to see if we shut down the reactor all of a sudden, will the still spinning turbine will be able to pump the coolant. So the generator at that time used to take some amount of time to start up, right? So how will you run the coolant in the time where you have turned off the reactor and the generator is still starting up? So their idea was that the turbine, which was spinning at high velocity, is going to continue to spin, although with a retardation, that is decrease in angular velocity, is going to slow down over time. But they thought that it will continue on spinning for some amount of time, and that can be transferred to the pump. So the pump will be able to cool down the reactor until the generator completely kicks in. But the problem was completely different, the xenon poisoning thing, which I'm going to be discussing later. But you understand how important a coolant is, right? So even in a reactor where you do not need to slow down neutrons, for example, a plutonium based reactors, you are definitely going to need a coolant. So in this case, the coolant is a lot of times some liquid metal. So for example, they use liquid lead, or they also use liquid sodium. So these reactors, the temperature of this reactor, or all the pipelines of this reactor is always needed to be at high temperature. For example, if you're using sodium, it has a melting point somewhere close to 90 to 100 degrees centigrade. So you need a continuous heater all the time, right? So why do we even go for a fast reactor? It has so much complications. This is the reason. Whatever U-38 you are having, which is in high proportion of all the ores, it will be converted into plutonium-239 when you bombard it with neutron, and that can be fissile in a fast breeder reactor. Now, breeder is a term that a lot of you guys might not be able to understand, but a lot of reactors, like I've said before, will be having a lining of non-fissile material but fertile material in the outer periphery, and these are basically being breeded to turn into something which is fissile, which might be used in the same reactor later by changing its position, or may be used in some other reactor. So yeah, that gives a lot of information to you guys. I've already talked about different kinds of moderators. So light water, heavy water, I think you understood. Light water is H2O, heavy water is D2O. And there's another thing called boiling water reactors. Some of the Indian nuclear power plants does have boiling water reactor. If I remember properly, I think Kudankulam is boiling water reactor. Yeah, most likely. I'm going to put it on the screen. And the last one is molten metal or molten salt reactor, which is used for fast reactors. Now, once these are clear to you guys, let us talk a little bit about fuel enrichment, which is an important topic that I definitely want to discuss over here. So the whole problem starts with your uranium ore, which is having only 0.7% of uranium-235 and 99.3% is uranium-238. So if you want to produce power continuously, even for that, you are going to require 3 to 5% of uranium. So if you look at uranium-233 and uranium-235, there's only one difference. What's the difference? The difference is the atomic weight, and one is 5 units heavier than the other. So the first method that they started to work with during the World War II, and this is the time of Project Manhattan, what happened in America. If I remember the place, yeah, it is Oak Ridge, Tennessee. So they created a uranium enrichment plant, and their method at that time was diffusion. So diffusion, what will happen is that I'm going to pass uranium gas. Now this might be a little confusing to you guys, but solid uranium, how are you going to diffuse anything which is solid? So what they turn into is uranium hexafluoride, UF6. Once this gas is formed, now you can pass it through a lot of membranes. So all of it will not be separated. A lot of times both U235 and U38 will be passing through the membrane because, like I said, the mass difference is very negligible. But because of that, they are having a whole array of these membranes, and these UF6 molecules are going to diffuse through them. And over time, after hundreds and hundreds of this passing, you are ultimately going to get an enriched uranium. You keep on doing it more and more, and you are going to reach somewhere around 90% of enriched uranium. So if you look at the formula of diffusion, it is very simple. Diffusion is inversely proportional to under root of mass. So mass is nothing but over here mass of uranium-235 or uranium-236, and you can look at it this way as well. Since 6 fluorine atoms are added, so the overall mass becomes even larger, and the fraction of U235 becomes even smaller. So now the mass difference is even smaller compared to what you would have as a just solid uranium-235 or 238. So diffusion is the rate is so less. So basically diffusion inversely proportional to under root of mass means that if you are having a lighter atom, then the diffusion will be faster, as you would expect, right? Now, if you do the simple calculation, you will understand that the improvement in every phase, and this is very well explained by a professor from University of Illinois, is that I'm going to link it down in the description box as well. So the improvement in every phase is only 1.0043. You get the point. So initially, if you are having a uranium-235, which is comprising of 0.7%, the next time it would be 0.7 into 1.0043. If you do the math, you are going to get 0.70301. So it's a very small fraction that you are increasing, and that is why you will need to do multiple of these diffusion through a lot of membranes. So it's a extremely slow process because what you're getting as an improvement is very less. It is like it is less than 1%. It is 0.43%. Now, because of that, this whole method of diffusion is obsolete now. Now what they use is something that some of you guys might have heard the name of, is the centrifuge technology. And what it does is that obviously if you're having two different elements, one is heavier than the other, the heavier element is going to spread in the outside direction, right? Because centrifugal force is proportional to the mass. Again, mass is involved, and again the problem is that the mass difference is very small between 235 and 238, right? So centrifuge, it does nothing but it rotates at a very high velocity, and the U38 part goes on the outer periphery and U35 stays in the middle, and you suck the U35 out. But the first time you suck it, it's not going to be like all U35. I think that much you were expecting. So that is why there are again series and arrays of these centrifuge machines, and there are thousands of these machines. Now, for the first time that I heard this, thousands of these machines, I was like, get out of here. That number is definitely wrong. You need to fix it. But then I found out that it only enriches it by a factor of 1.5, which is much better than 1.0043. But if you look at that, then that factor is still not that much. So that is why you really require thousands of these centrifuges to over time get even 3 to 5 percentage of enriched uranium, which is having like 3 to 5 percentage of U-235. And that is the thing that I was talking about. This is the same technology of reaching it up to 90% as well. All you need to do is keep on running this process for a longer duration and more machines, more arrays, and you're over time going to reach the weapons grade uranium, which is the problem that a lot of countries which do not want new countries working on uranium technologies be dabbling with. And that is the whole area of debate. So that's pretty much, that gives you a good idea of what is uranium enrichment. It is a big roadblock to any country which is trying to produce weapons grade uranium, which is a sigh of relief to a lot of countries which already has weapons grade uranium. So you can have the mastery of nuclear fission technology. A lot of countries which do not have nuclear bombs have nuclear technology for power production, but this is the one segregating part which is going to give you access to nuclear weapons, that is the uranium enrichment. It's a very important topic to be discussed over here. And apart from that, see, like I said, that uranium-238 is not fissile, but it is fertile. And in a similar manner, there's something else which is not fissile but is fertile, and you guessed it, it's called thorium. So thorium has an atomic number of 90, and when you bombard thorium-232 with a neutron, what you get is uranium-233, which I have talked about before, is fissile. And that is another way of producing power. And India has a massive resource of thorium, but this technology is fairly new. And since India is one of the very few countries which is new in this technology, which is having an abundance of thorium, and because of that, India has to take the initiative to do the research on this one if you want to become self-sufficient when it comes to energy production. All right, so that's pretty much all that I wanted to discuss over here. A lot of information, I understand. Let me know down in the comment section what you liked about it and what you did not. My information giving process was very solidified on that. I want to make people learn about this whole nuclear technology in a simple manner. Let me know down in the comment section whether I was able to do it or not, because your review and response means a lot to me. If you want to learn how to improve your communication skills, speaking skills, then Art of Speaking course is one that I'm running. I have been running it for over 1.5 years, and I'm never going to stop it. The course is focused on improving your communication skills, speaking skills, and confidence, which I believe is an important aspect of anyone's life. You must be thinking that all of a sudden we're talking about fuel enrichment. How did he get into Art of Speaking? Well, we are closing it, and I want to let you know about few of the courses that I'm running on my own for a long time. You might not be knowing about it as well, because I do not promote a lot about it, and I want only people who are extremely dedicated to get into it, because some of you guys might be expecting, not you guys because you reached the end of the whole podcast, but some of the people expect a easy pill to improve at anything. But you guys know that since you have to learn something, you have to get to the bottom of it to the end of the podcast. In a similar manner, you would also be knowing if you have to learn a skill, let us say speaking or spoken or communication skills, then you'll have to put a good amount of effort. But the direction is important, and that is why I'm running this course. If you want to know more about it, link will be down in the description box. With that said, I want to discuss one tiny question related to simple basic engineering that would be very fascinating to some of you guys. Now, this is a question that I shed some light to before in the previous episodes as well, but here we are finally going to discuss the answer. Now, the question goes like this. See, this wire that you see over here is made of leather or rubber, all right? And just below that is the boom arm, which is made of steel. Now, if I touch this rubber, it is going to feel hotter as compared to the steel. Or you can take an example of a spoon. The spoon is always going to seem a little bit colder than this wood that the table is made of. The question comes is that, do you think that spoon is at a lower temperature compared to the wood of this table? So what do you think? The answer is that no, that is just not possible. Both are at the same temperature, because what we are talking about over here is thermal equilibrium. If at any point two different bodies which are in contact, which can exchange heat, so even if this part of metal and the wood of the table, which is not visible right now, is not in direct contact, it is in the contact through the air in between. So there can be heat transfer in terms of convection. So they are connected, and whenever they are, then there will be heat exchange between these two. And one of two things will happen. Either they are at two different temperatures and heat transfer is taking place and it's in a transient stage, or all the heat transfer has taken place and both are at exactly same temperature. So if that room has been in that condition for a long time, then every particle or body in that room is at same temperature. Otherwise, heat transfer will take place, and will take place until unless all the temperatures are equal. So when I talk about this part of the mic and this part of the mic, both are exactly at same temperature. This made of plastic and this made of steel might seem like at a different temperature, but that's not the case. Both are exactly at same temperature because these are in contact. There will be conduction going on, and it will be going on as long as it takes for them to reach the same temperature. You can also think about it like this. Do I have a cup over here? Yep. Advertisement of Momentum Podcast. So see, if I put cold water into it, all right, chilled cold water into it, and the next thing that I do is that I pour very hot coffee into it. So those two are at different temperature. There will be some instability when it comes to thermal. What we call is that it is trying to reach thermal equilibrium, but it will take 5 minutes, 10 minutes, maybe half an hour. But over time, don't you think that both the fluids will attain the same temperature, including this cup itself, right? All of them will remain at the same temperature after, let us say, half an hour or so. That is what we call thermal equilibrium. And that is what any body would want to reach. Any body would want to reach thermal equilibrium, chemical equilibrium, mechanical equilibrium. There will always be these equilibriums present given sufficient amount of time. So in a room, when you talk about a spoon and the wood of the table, they are both at same temperature because you have given them sufficient time to reach the thermal equilibrium. But the question is that why are they seeming like they are at different temperature? Why does it seem like wood is at a higher temperature and spoon is at a lower temperature? The answer is that your body itself is the only thing in that room which is not in equilibrium. Your body is always going to be at a higher temperature. The general body temperature is somewhere around 36 degrees centigrade. And the reason for that is because your body is functioning. There are a lot of things going on. There are organs that are operating, and body requires a certain amount of temperature. Blood is flowing through your veins. The only human being which is in equilibrium with the environment is a dead person. When a person dies, that person turns cold. Because of this reason, because all the organs and all the blood flow has finally stopped, and because of that, that body will also want to attain the same equilibrium. And that is what your body is continuously fighting for. Your body is continuously trying to maintain that higher temperature so that your body and the organs are functioning. So your body is at a higher temperature. So now when you look at it this way, a higher temperature hand touches my mic over here, which is having a steel surface. What do you think is happening? All of a sudden, heat transfer takes place, and that part which is touching the mic will try to reach the same temperature, right? As long as it is touching over here. So over here, what is happening is what we call heat transfer, okay? And let us take another example. Let us say the cover of this phone is made of plastic. So now when I touch it, then again heat transfer is taking place, because this is again at room temperature, let us say 26 degrees centigrade. So this is at room temperature, I touch it, heat transfer again takes place. Alright, that's fine. Heat transfer takes place with steel, heat transfer takes place with plastic. You are at a higher temperature. These two objects are at a lower temperature. Heat transfer takes place in both the cases. Why the hell am I feeling that this plastic is hotter compared to this steel? The answer is that the rate of heat transfer will be different. And that depends on the conductivity of the material that you're touching. So when you're touching a spoon, the spoon is made of steel and the conductivity is high. And because of that, the heat transfer between your hand and that steel is faster. The rate is higher. And that is why you feel it to be a little colder, because you are losing heat faster. Compared to, let us say, a plastic, it is an insulator, so it is having lower conductivity. So heat transfer between your fist or hand and this plastic is going to be slower. So you are going to be losing it slowly. And because of that reason, you feel that it is hotter and you feel that the spoon is colder. Got the point? So it is all about feeling, not about what actually is. So to conclude, are they at different temperatures, the spoon and wood? No, they are at exactly same temperature. Why? Because of thermal equilibrium. Okay. Also, tell me, why do I feel that spoon is colder than wood? Because the rate of heat transfer between spoon and you and between wood and you are different. Spoon and you is higher because spoon is a better conductor and heat transfer rate is faster. Got the point? All right. So these are small basic mechanical engineering that every now and then I want to discuss. And let me know if you have further questions related to this. I think that I'm going to make it as a part of Spacecast. And that's about it, guys. You want a lot of bunch of information, be over here weekly. We are going to share a lot of them. You have some questions related to space science, astrophysics, related to nuclear science, related to mechanical engineering, related to physics. Let me know down in the comment section, guys. These are going to be discussed on a regular basis. I am not going to stop doing it. I've been doing it for over a year. It's only that's every now and then I have so much work that I slack off. But like I said, your boy made a lot of money. Now he has a lot of time to do what he wants to do, and Spacecast is on the top of that list. I'll see all of you in the next one. Think about art of speaking. Link is down in the description box, and I'll see all of you in the next one. Till then, bye.